Hello everyone, my name is Nikola Marinčić. Welcome to another class of our course, An Introduction to Machine Intelligence for Architects and Other Non-Engineers. We are still in the week number 9, but I have split this video so it doesn't get too long. This is the second part of the video, where we will try to implement a flexible neural network algorithm by using linear algebra, by implementing it in NumPy using vectors, matrices, and operations such as dot products, matrix product, and so on. Our goal is to create an algorithm where we can freely specify how many layers of a neural network we want to have and how many neurons per layer we want to have. So we want to be able to choose that. Once we do that, everything else should be done by itself, so automatically. How can we implement such an algorithm? Well, for this to work, you really need to know Python and know how to write code, and we need to go and reach another higher level of abstraction than what we have been doing so far. So let's start doing it. We start with the exercise number 13, which is named Parametric Neural Network Implementation using Matrices. Okay, let's just initialize our libraries. This is our dataset, very similar to the one before. As you can see, you have yellow points, blue points, and green points, which are encoded by numbers 1, 2, and 3, which are our labels. We already have the function sigmoid and convert label because we did it last time. There is no need to repeat this. And the first task will be to normalize data. This is also what we learned. We'll just do it quickly. So normalize the data by subtracting the respective mean from each data point's components and dividing each data point's coordinate by its respective standard deviation value. All right, so data, and we want to subtract from it data.mean of the axis 0. So we get this, then we put it in parentheses in order to divide this whole thing by data standard deviation, std of the axis equals 0. So these are our new data points. Let's just store them in the variable data again. Okay? And then plot the normalized data set, plot data labels. As you can see, it looks almost the same as before, and it's a little bit different than the last data set we have been working here. It has another data point here, which should make it a little bit more complicated for the network, because the network needs to really bend the space in order to make these points belong together. Before we can implement this algorithm, we need to know Python and NumPy a little bit better. We need to know how are Python's mathematical operations different than NumPy's mathematical operations. And let's examine the task number 2. So it says create a NumPy array of 5 numbers and store it in a variable mp_lst. So mp_lst is equal to mp array. And now I just want to put a couple of numbers here. So 3, 1, 5, 3, 7. These are 5 numbers, yeah? mp_lst. As you can see, I got a NumPy array containing 5 numbers. Now it says create a typical Python list of 5 numbers and store it in a variable lst. So this is something that we have not been doing so far. So I will just show you, it's very easy. lst is equal to, just open square brackets and put the same numbers. 3, 1, 5, 3, 7. lst, and you get the plot. As you can see, it's different. Here you get this array thing, and here there's nothing else, just our values. So this looks nicer when it's printed at the moment. But let's see if there's something different about these data structures here. Yeah? Next task is to add the value 1 to each element of both lists. Well, with NumPy that's kind of easy. So mp_lst, this gives us the data set, and I can just type +1. And this will happen automatically. So each value, what used to be 3 now is 4, what used to be 7 now it's 8. So we added 1 to each element of these lists. Quite straightforward, but let's do it with lst. So lst, which is this one here, +1. It doesn't work. It says can only concatenate list, not int to list. Okay, so it doesn't work. List in Python does not contain only numbers, or does not have to contain only numbers. It can contain strings, it can contain objects, it can contain different data structures within itself. It can contain NumPy arrays themselves. Yeah. So it's a more general structure, so mathematical operations on it do not work by default. Let me show you how this works further. So it says multiply each element in both lists by 2. So we have mp underscore lst. If I type times 2, I will get all of the numbers multiplied by 2. So what used to be 3 now is 6. What used to be 5 now it's 10. Yeah. And if I do this to lst times 2, I get something a little bit weird. So what I get is my list used to have numbers 31537, and now it has 31537, 31537. So it just concatenated actually another list to it containing the same elements and put it at the end of the original list. Yeah. So it works quite differently. It definitely does not multiply the numbers within the lists as expected. But now there's another way how we can actually achieve this by using normal lists, and this is by using so-called list comprehensions, which is a very powerful concept in Python. So how does this work? It says use list comprehensions to add value 1 to Python list lst. If you have never done this before, and I assume some of you will not know this, the easiest way for me to explain how list comprehensions work is to show you by means of a for loop. So we have a list lst, yeah? It has 5 elements. How would we iterate through this list in Python? So I would say for example, I is in an element, I in lst print I. Yeah? And I get this element. So I gets assigned to each element of this list, and one by one they are printed. So we get 3, 1, 5, 3, 7. Yeah? 3, 1, 5, 3, 7. The order remains. Yeah? So what I can do now is take this I, which is getting printed, yeah, and put it before here. And I get I for I in lst, yeah. And if I just put this expression in square brackets, I get a list comprehension. So this is a list comprehension. When it is in square brackets, it will produce a list from this iterative sequence. So it will assign I to each of these elements, 3, 1, 5, 3, 7, and then it will return the I untouched as it is, yeah? So when I run this, I just get back the same list, so lst, and this gives me the exactly same result. But this here is more flexible, because here now I can say, instead of I, which is intact, I can just say I plus 1 for I in lst. And what I get is I get I, and then in the next step I'm increasing this I by 1. And then from these increased elements, which are these elements here, I create a new list, which is this. So now I have a list which contains all of the elements of the old list increased by 1. And I can also say increased by 3. No problem. And I can do many more things. Yeah. Now it says use list comprehensions to multiply each element of the Python list by 5. So let me again show you how I would do this by using for loops, how I would do this iteratively. So for I, it doesn't need to be I, it can be element, yeah? For element in lst, print element. So I get 3, 1, 5, 3, 7. So if I wanted to multiply each of these elements by 5, I would say element times 5, yeah? And I get 15, 5, 25, 15, 35. So I just need somehow to put this in a list comprehension. So what I can do is just take this element times 5, place it here. So element times 5 for element in list. And I should just erase everything else. And I have created a list comprehension. Now all of these numbers should be within one list. And there you have it. Element times 5 for element in list. This can be also A times 5 for A in list. So this can change, yeah? It can be B times 5 for B in the list. This is not important. As long as this is the same thing, whatever you choose B to be, it will be multiplied by 5 and added to a list. Now let's go a little bit further. It says add another number, 8, to both lists. So I have, let me remind ourselves, so we have mp underscore list, and we have lst. They have the same elements. Add another number 8 to both of these lists. How can I add a number to NumPy list? Well, I can use a NumPy command np.append. I will add the old list, comma, what I want to add to it. So I want to add the number 8. What I get is the old list with 8 at the end. Yeah. And then how do I do this to LST? Well, I just say lst.append 8. And nothing happened. That's why I'm asking here, print values of np list and lst. Well, if I say np lst, I would expect it to have this 8 added at the end, yeah? But it doesn't have the 8 added at the end, because NumPy lists are immutable. You cannot actually add the element to the list. What this command does is create a new list from the old one and adds one element when creating this new list, and then gives you back the new list. So you actually cannot change the old list. It's called immutable because it remains untouched, as you can see here. Yeah. If I really wanted this new element A to be there, I would need to overwrite this variable containing our old list. So np lst will need to be overwritten by this new list. And now if I ask what is np list, now it has 8 at the end, yeah? Because we overwrite it. But our lst is a mutable list, yeah? So now our lst has 8 in it. So when I do append, I add a new element to it actually. I don't need to overwrite anything. If I do it once more and plot lst, you will see that I have added it once again at the end. If I wanted to remove an element from it, I could do lst.pop. Yeah? And if I plot lst now, you'll see that it has only one 8. If I do pop again, now it doesn't have 8 anymore. Yeah? Okay, let's do something more. Initialize an empty Python list, store it as lst2, append to it the number 5, and print the content. So how do we create an empty list in Python? So lst2 is just going to be equal to square brackets and nothing in it. Yeah. If I now type lst2, there's nothing. It's an empty list. But it says append to it number 5. So append 5. Now, when I type lst2, we have 5 in it. If I do it again, I have 5 and 5. I do it again, I have 5, 5, 5. Yeah? Okay, this is clear. So we need to know how to initialize an empty list and how to then add things to it. Now it says lst3 is a list containing 8 integers. So 1, 2, 3, 4, 5, 6, 7, 8. It says return the first 3 elements of this list. So it should return 1, 2, and 3. How do we do this? Well, with using indexing. lst3, I can use square brackets to index this list. So I can, if I say lst and put colon, I get all of the elements, yeah? But I can use the colon to actually define where do I want to start, when do I want to stop taking the elements from this list. If I say column 3, then this will give me first 3 elements. If I say, okay, it says return all the elements of this list after the third, which is what I wanted to show you, I can just say lst3, 3, colon, and then I get 4, 5, 6, 7, and 8. So I get elements after 3 or after 2 if I want, yeah? After any number. But this should be able to work also not only from start to back, but also from back to the start. So the next task is to return the last element of the list. So lst3, and if I put the number -1 within the brackets, I will get the last element, which is 8. Yeah. Now it says return the last 3 elements of the list. How can we do this? So lst3, to get the last elements, we want to have it from the -3, which will give it the third from the back, and then all the way till the end. And you get 6, 7, and 8. If I do -4, you get last 4 elements, yeah? So this is incredibly useful. And this is why Python is such an elegant language, because you can do operations like this. Finally, we are now ready to implement our flexible neural network. And we will first do it step by step, and then we will create a fully working algorithm. Step by step is more important to master. The rest will be just copy-paste. First task is to create a variable sizes that will store a list of numbers. Alright, each new number indicates a new neural network layer. So it means that if you have 5 numbers, we will have 5 layers, yeah? And the value of the number, which means if it's 1, 2, 3, 4, 5, or 1 million, this will indicate the number of neurons in that layer. So how does this work? I can just type sizes, make a list, and if I have xxxx numbers, this means I will have 4 layers of the neural network. And now I need to define how many neurons there are per layer. So in the input layer, our data has x and y coordinates, yeah, which means only need 2 neurons in the input layer. And in the output layer, how much do we need? Well, our data is marked by 3 types of labels, yeah, 1, 2, and 3. So it will be good to create a neural network architecture which has 3 outputs in the output layer, because it's going to be easy to implement mean square error on top of this. So I will just add it 3 layers in the end. But now this is up to me how many elements do I want to have, or how many layers do I want to have. Do I want to have more layers here? Yeah, I can just do this. So let's have it. Let's keep it with 4 layers, because it will be too much printing on the screen if you have more layers, especially if they're big. So let's make next layer have 3 neurons, and then the next layer have, for example, 5 neurons. This is how we will encode the size of this neural network. Yeah, sizes. And this is a normal Python list, not a NumPy array. Next task, it says combine elements of the variable sizes to indicate what sizes of matrices containing weights and biases we need to instantiate. So what do we know? This is the first, or the input layer. It doesn't have any weights and biases associated with it. But these 3 layers do have, yeah? So for biases, we know that in this layer we need 3 biases, in this layer we need 5 biases, and in this layer we need 3 biases, yeah? How can we operate with the variable sizes to express this? So we can say sizes. If we just say sizes and put colon, we get all of the elements. But we do not need 2, yeah? Because in the first layer there will be no biases. We can just discard this number. We can say, give me everything after the first number. And then I get 3, 5, 3. So first layer that will have biases will have 3 biases in the first layer, 5 biases in the second layer, and 3 biases in the last layer, yeah? But how would I do it for the weights? So what I know is I have 4 layers, and in the weights, concerning weights, here we have 3 neurons, and the last layer has 2 neurons. So our weight matrix will be of the size 3, 2. So it will have 3 neurons, and in each neuron we will have 2 weights, yeah? So we need matrix of the size 3, 2. So how can I make then 3, 2? Well, what can I do is I can have one list which starts with 3, then goes to 5, and then goes to 3, which is this one. And I can have the second list starting with 2, going to 3, and then going to 5. And then when I combine these 2 lists, I can actually get the right sizes of my weight matrix. So I can do sizes of everything before the last element, and I get 2, 3, and 5. So I get 2, 3, and 5, and I need to combine it 3, 5, and 3. How do I combine them? Well, what I know is that second layer will need a matrix 3, 2. This layer will need a matrix 5, 3, and this layer will need a matrix 3, 5, yeah? So I can now just combine these 2 lists to get the appropriate size of my matrices. So it says here, make a list comprehension returning the required matrix shape for biases. Well, for biases it is easy, I just need this one list here, yeah? Size is 1. So let's just do it first by creating a for loop. So for a in sizes, print a. So 3, 5, 3. But the matrix shape is not going to be only 3, it's going to be 3, 1. So I need 3 rows and 1 column. So I can just type 3, a, 1. So 3, 1, 5, 1, and 3, 1. This is correct. And now let's just make this into a list comprehension. So take this thing a comma 1 for a in sizes. And just put this in a 1 in square brackets. And there you have it. So this is a list comprehension which gives us the correct sizes for all of us bias matrices. So 3,1, 5,1, and 3,1. Because we have here 3 neurons, 5 neurons, and 3 neurons. So this will work. Now it says instantiate all the bias matrices and store them in a variable biases. Well, how can we do this? Well, it's very easy. We have this list comprehension which gives us the correct sizes. And this here, a comma 1, will be in the first iteration replaced with 3,1. In the second iteration replaced by 5,1. In the third iteration, it will be replaced by 3,1. And this is actually the shape argument when we create our matrix. Remember, when we create our matrix, mp.random rand n, we say, for example, 3,1. Yeah? And then we get a matrix which has 3 rows and 1 column. Well, this thing is the same as this thing in it. So we can just say mp random rand n and put this as an argument. And this should give us all of the biases at once. And there they are. Well, maybe this is not very clear what's going on here, so let's make it a little bit nicer. First, we will store this into biases variable. Yeah. And now let's just loop through this biases variable that we have created. So for b in biases, print b. Okay, a little bit better, but still it can be improved. So I can put here an empty row. So now you can see this would be then layer 2, this will be layer 3, and this will be biases of the layer 4. If we wanted really to print layer 2, layer 3, layer 4, we can do this. We can use, for example, a function called enumerate. So what enumerate does? Let's say that we want to enumerate biases. Enumerate biases. When we do this, we are joining an index of this iteration to whatever b is. So now b is a single bias matrix, yeah? But it is joined with an index 0. So we can split this by saying for e or I or any variable I comma b in enumerate, and now b remains what it used to be, but now we have I, which gives us the index of this iteration. So let's print, for example, I before. So print I, and this gives us 0th iteration, first iteration, and second iteration. So if we wanted to make this into a layer of our neural network, then we know that this should be second layer, third layer, and fourth layer. So we can just say I plus 2. Then we get layer 2, layer 3, layer 4. We can still improve this by saying something like this. Layer, and then put this in these kind of brackets, and we get layer 2. These are the biases of layer 2, biases of the layer 3, and biases of the layer 4. And we can reuse this thing here for example, browsing through our weights when we have them. Okay, now it says use the function zip to print the necessary matrix shapes for weights. Where do we have our matrix shapes? Well, we have our sizes 1, and we have the sizes until the last element. And by combining these two lists, so first element of this list with the first element of the second list, second element of this list with the second element of the second list, and so on, we can get the necessary sizes of our weights matrix. So how can we do this? Well, let's make this zip first. So zip, and then what do we zip? This first, yeah, 3, 5, 3 first, and then 2, 3, 5 second. We zip these two lists, and then zip combines these elements. First element with the first element, second element with the second element. To iterate through it, we can make a for loop. So for a comma b in zip, print a comma b. And now we have it. So we have 3, 2, 5, 3, and 3, 5, which are exactly the sizes of our weight matrices that we need. We just need to make this into a list comprehension. So how do we do this? We take this a and b, and we put it here. So A and B for A and B in zip sizes, and put this in square brackets. And here it is. This is our list. Now we have the right matrix shapes for our weights, all of our weights, yeah? So actually I did it already here, so I can just copy paste it. Here is a list comprehension returning the right things, and here I will leave it as a loop. So print A comma B. Yeah. Let's go to the next task. It says instantiate all the weight matrices and store them in the variable weights. Well, the same thing that we did with biases here, yeah, we can do with weights. So we can just initialize a matrix of randomly initialized numbers with coming from a normal distribution, and just plug this thing as a kind of shape that it needs to create. So how can we do this? We just need this, and here we say mp.random rand n, and there you have it. All the necessary weights in 3 different matrices with the right sizes in one single Python list, and just store it in variable weights. Yeah. And now we can use this construction here that we used before to just print it out nicely. For I, B in enumerate not biases now, but weights, let's just print it. I made a typo. Yeah. And there you have it. So now you see that the layer 2 has 3 times 2 matrix, so 3 rows, 2 columns, because the layer 2 has 3 neurons, as we have specified here. Yeah. The next layer should have 5 neurons and should parameterize 3 activations from the last layer, so it should be of the shape 5,3. And it is indeed in shape 5,3, so 5 rows, 3 columns. And the last one should be of the shape 3,5, so it should have 3 neurons and parameterizing 5 activations from the last layer, so 3,5. And indeed it has 3 rows and 5 columns. So this works. We have all of our weights and biases instantiated into only 2 variables, which is pretty amazing. Now it says transform the first data point into a column vector and store it in a variable d point. So we have our data. First data point is a point with the index 0, as we did many times. We just need to reshape this into a column vector, which has 2 rows and 1 column, and store this in a variable d point. Okay, here we go. Now we need to do the same thing with the labels. So transform the label belonging to the first data point by using the function convert label and store it in a variable y. So we have labels. First label is 1. We need to convert it. So convert label. We already implemented this in the beginning. Fine. And we need to store it in a variable y. That's our label for the first data point. Now we need to compute the forward pass. And we have the forward pass equations here. So it will be relatively easy to do this with these equations in front of us. But before we do this, what we want to have? We want to have a list of all the activations, like we have a list of all the weights. Yeah, this is all the weights, all the matrices stored in one list of weights, and all the matrices of biases stored in one bias list. We want to have the same thing with our activations. Yeah. And also with our weighted sums. But the problem is activations, we have not computed them yet. We only have the first activation, which is our data point. So we need to create an empty list for activations and weighted sums. And then one by one, when we compute them, we need to fill them with values. And these values will be matrices containing all the activations and weighted sums. So let's create an empty list for activations. And let's create an empty list for weighted sums. Weighted sums. Okay, Now it says compute the forward pass and print the result of the last layer activation. Append all the weighted sums and activations within the respective list. Well, let's first compute the forward pass and then we will see how can we actually append all of these things. So what do we need to do? We have our first activation and we will call it A. Why don't I call it A1? Well, that would be the problem, yeah? Because if we want to have a very flexible algorithm, we should not be naming, hard coding the names of our activations because we want to reuse the variable A as we compute through the next layers. We want to store it in the same variable A. So we always want to have the variable A for activations, variable W for weights, and variable B for biases. We should not change their names. There should be only one name and the values in it should change. It should be updated. So we will then instantiate A to be our activation. And since we are starting from the first layer, we need the first layer activation. And the first layer activation is our data point, which is D point. Yeah. So our A is the first activation. Yeah. Activation of the first layer, which have two neurons. So first activation, second activation, X, Y. What then? Well, we need to compute the activation of the next layer. How to do that? Well, we compute this dot product, we compute this Z, which is a dot product of W and A of the last layer, and add B to it. So how do we do it? We say Z is going to be equal to dot product of weights and biases, NP dot. But what are our weights and biases? That's the problem. Our weights are now stored in a variable weights, and this is a Python list which contains 3 groups of weights and biases, yeah? Also, biases is a Python list containing 3 matrices of biases, yeah? So we need to iterate actually through our weights and biases, yeah? So weights, yeah, and biases. We need to iterate through them. So we need to compute the activations of the layer 2. We need the weight matrix of the layer 2, yeah? Dot product of this matrix with the activations of the last layer, which is this thing here. And to it, we need to add the biases of the layer 2. So we need to iterate through these weights and biases variables. So how do we do that? Well, since always we have weights and biases for the certain layer, which we join together, we will just make a zip out of them. Yeah. So let's do like this. So zip weights and biases. So if I do a for loop, I can say for W, B in of zip, I can then print W and B. So I can just first print W, then an empty row, print biases, print an empty row, and then, for example, make a line, yeah, just to see what's there. Okay, so we have now weights of the layer 2, biases of the layer 2, weights of the layer 3, biases of the layer 3, weights of the layer 4, biases of the layer 4. So we need to combine them. How do we combine them? Well, we need to compute, for example, Z. What would be Z in the first layer? It would be weights of the second layer, so which is W, because W will start with this value. Actually, let's call it capital W, because this is the convention that we use so far. So we need the matrix product, so NP dot of these weights and with our activations, and our activations are stored currently in A, yeah? And to it, we need to add the biases, so plus B, and these biases should be added to it. Then we have computed Z. Let's print Z. What will happen is we will have an error, but before we have an error, we will have actually computed Z for the second layer. Yeah? Why do we have an error? Because A remains what it used to be, activations of the first layer. And then when we started computing activations of the third layer, we need to compute dot product of the layers of the third layer with the activations of the second layer. And we don't have the activations of the second layer, so it multiplies them with the activations of the first layer. And there is an error because the sizes don't match. So we need to update this variable A actually with the new value of A after this first loop. So how do we do this? Well, we say that A is going to be now, what? It's going to be sigmoid of z. Now, after that, I will just print A. As you can see, now A, in the first case, I will just print an empty line. A starts being this in the first loop. In the second loop, A becomes this. And in the last loop, A becomes this. And as you can see, this is the activations now of the second layer, activations of the third layer, and activations of the fourth layer. So if we wanted to fill our activations, we can use it. We can just append this A to it. Yeah. But before we do this, it needs to be clear to you that with this for loop, we cannot compute the activations of the first layer, because activations of the first layer is the data points itself. So we need to manually add the first point, the first layer to our activations. So I will say activations is going to be equal to d point. So I do this manually. And now if I ask what are the activations, then we have our first activation, which is the data point. Okay, now I can keep appending with this for loop to fill the others, yeah, to fill this one, and this one. How do I do this? Well, I can just say activations append A. And in the same way, weighted sums, they do not exist for the initial layer, so I do not need to do anything there. I can just append to it weighted sums append this z here, yeah? And I don't need to print anything else. This will now completely compute the forward pass. Let's see how this works. So I can now say activations. I have them. Again, they don't look nice, but I can use this construction here to actually print them. This for loop here. So I can say for I, B in enumerate activations, print the layers. And now the layers are kind of different because we start now from the first layer, so I will not use I plus 2 anymore, I will use I plus 1 to actually name the layers correctly. So we have layer 1, we have our data points. Layer 2, we have activations. Layer 3, we have activations. And layer 4, we have activations. And we can do the same for weighted sums. So weighted sums. But now I need to put back this I2 because we have one layer less. So then these are the weighted sums of the layer 2, weighted sums of the layer 3, and weighted sums of the layer 4. So we have everything for the forward pass. That's very nice. Now it asks us print the last activation. So activations, all of them. How do we take the last element of our list? Well, we learned how to do this before. We just use the index -1 in the square brackets. Next, -1 gives us activations of the last layer. So -1 now gives us last layer. And we have them, activations of the last layer. If we have them, then it should be very easy to compute the cost for this data point. So it says compute the cost of the first data point of the last for the last activation and store it in a variable C. So we have activations of the layer 1, and we simply subtract from them what? We subtract the labels, and we can subtract them because they are of the same shape. So we can say activations of the last layer minus y. We get the error for this data point for all the components, and we want to square this error to have the mean squared error. So I can just do this times 2, which is the same as multiplying this thing by itself twice by using Hadamard product. And now this is the cost of the first cost for the first neuron of the output layer, cost for the second neuron of the output layer, and cost for the third neuron of the output layer. And we want to minimize this cost towards our label. So to compute the total cost for this particular data point, we just need to do np.sum of these three values, and we get that the total cost for this single example is 1,03, and we will call this C. Yeah. Okay. Now comes the interesting and a little bit more challenging thing, which is the backward pass. But still, it shouldn't be too hard because we already have all of our equations here. Yeah. So it says create variables d weights and d biases that will store partial derivatives in terms of weights and biases in all layers. they should have the same size as the corresponding weight and bias variables. Well, that's kind of obvious if we have our weights. Actually, let's copy the whole thing here. Oops. If these are our weights of all the layers, we need to store also the partial derivatives in terms of these exact weights. And we need a data structure which will be of the exactly same shape. So we just need to recreate another list of matrices, but which will contain 0 in each of these positions, yeah? Because when we compute the actual derivative, we need to store it into these kind of placeholders. It actually doesn't need to have zeros, it can have any numbers if we overwrite it, but it's the safest bet to just put zeros in there. So how can we actually do this? Well, we know that our weights is a list of matrices, so we can iterate through it. So let's say for W in weights print W. Okay, we now have the same thing as here, but now I can say what is the W comma shape, and now I get the shapes of all the matrices within this list of weights. So 3,2, 5,3, and 3,5. Yeah. Let's just make a list comprehension out of this. How do I do this? I just put this here. W shape for W in weights and put it in square brackets. Now I get all the shapes of our weight matrix. Yeah. And let's do this also for biases. So B shape for B in biases. We have now correct shapes for our weights matrices and for our bias matrices for the storing partial derivatives. So how do we actually make them into 0 matrices so that all the elements within these matrices are 0? Well, we can just initialize so-called 0 matrix. So mp.zeros. If we put a shape, for example, 2, 3, we get a matrix of zeros which has 2 rows and 3 columns. So we can just say mp zeros of this shape, mp zeros of this shape, and we get all the weights. Actually, we get placeholders to store partial derivatives in terms of weights, and we can do the same for this biases here, and we get it. Now let's just use this same piece of code here to iterate through it in the same way as we do for weights. Instead of this time, we will call this D weights, yeah, and this one here we will call D biases, yeah. And now we need to iterate through D weights. As you can see, we now have two data structures. One is containing partial derivatives in terms of weights, and one is containing weights. And this one has only zeros, so we will know when we fill it what needs to remain to be filled, what we have filled already, and what we need remain to be filled. So this is why I put zeros in it. And we can do the same for biases. Yeah. For I, B in enumerate D biases. We also have our biases here. So these are the biases which are empty now for our layers. If I do the same for our normal biases, I just need to make sure to erase this thing. And now you can see these are our actual biases. These are the placeholders where we should put partial derivatives in terms of biases. These are our actual weights, and these are the placeholders where we should put partial derivatives in terms of weights. So we kind of have the data structure ready. We just need to fill it. So it says compute the partial derivative of the total cost in terms of the activations of the last layer and store them in a variable DC. Well, the cost is C, yeah, but the DC will be derivatives in terms of the cost, which will be just 2 times activations of the last layer minus Y. This is the formula. So DC, we now have partial derivatives in terms of the outputs before the cost. And now we need to compute the partial derivatives of the activations of the last layer in terms of the weighted sums of the last layer and store them in the variable delta. Well, last time how we did it is we did delta of the layer 3 because 3 was last layer. And now if we did delta 4, we would be hard coding again our partial derivatives in terms of the weighted sums. So we cannot do this. We just need to use the variable delta and then iterate somehow to replace what delta is for each of these steps. So how can we instantiate delta? What would be delta here? Well, delta starts by being partial derivatives of the total cost in terms of the weighted sums of the last layers. So how do we compute this? We have already partial derivative of the total cost in terms of the activations times, what do we need to add to it? Well, we need to add the activations of the last layer times 1 minus activations of the last layer, because this is actually derivative of the sigmoid function. So activations of -1, which is the last layer, times, I'll just copy paste this, 1 minus activations of the last layer. This should give us partial derivatives in terms of the weighted sums of the last layer. If you don't remember this formula, you can find it here. So partial derivatives of the total cost in terms of the last layer is 2 times activations of the last layer minus labels, and then Hadamard product with the activations of the last layer times 1 minus activations of the last layer. And this is what we effectively have computed, because I first computed DC, which is 2 times activations minus Y, and then add the Hadamard product with the partial derivatives of the weighted sums of the last layer, which gives us this, delta. Okay, now that we know partial derivatives in terms of the weighted sums of the last layer, we can just automatically deduce what would be the biases of the last layer. So we can say that the biases of this very last layer, yeah, -1, will be the same as delta. Yeah. So once we did this, we can try to plot to see what they store now. So where did we do this? Well, we did this here, but if I run this piece of code, I will just override them back to what they were before. So I just need to make sure to use only this for loop here to check what's now in D biases. So if I go to D biases now, you can see that now we have successfully filled the last layer, yeah, with this step here and this step here. We have filled the last layer, but we still need to fill the weights of the last layer. So how do we do that? It says compute the weights of the last layer and store them in the variable D weights. Well, we have defined here a formula, if you don't remember. Partial derivatives of weights in any layer can be computed by doing a dot product of the weighted sums of that layer with the activations of the layer before it transposed. Okay. How do we do this? So we need to compute the dot product of the partial derivatives in terms of the weighted sums of the last layer, which is this delta. This is how delta started, what delta started being. So delta with the activations of the layer, which is the layer before it. And the layer before the last layer is, in this case, layer number 3. So how can we then index this layer number 3? So we can say activations of the layer 3, but this would not be ideal. We can just say -2, so second from behind. So, and then we need to compute this activations transposed, and then we get all the partial derivatives of the weights. So we have them here, but we need to store them in our data structure here. So we need to put them in this 4th layer here. So we need to put them in this variable D weights. How can we do this? Well, we just need to say, we cannot say D weights equal to this because it will overwrite it. It will just, D weights will just become this matrix. We need to say D weights of the last layer is equal to this. Yeah. Now let's see what this thing has in itself. Here we plotted all the elements of this matrix containing partial derivatives in terms of the weights. So we can just take this for loop to check what is it in it now. So let's just do this now. As you can see, we now filled all the elements in the weight matrix of the layer 4. We just need to do this for the layer 3 and for the layer 2. So we need to somehow iterate backwards to first fill 3, then when we know the delta of the 3, we can use it to compute the delta of the 2. When we know the delta of 3 and 2, we can compute weights and biases of the layers 3 and 2. So how do we do this? Well, this is something where you really need to a little bit know how to program. And also you need to test this a couple of times before you find the right way to do this. But it says here, to start, instantiate the variable number of layers, and in it store the number of layers of the network. Use it to update the rest of the weights and biases. So this is the most complicated part here. So what layers do we have in our network? Well, we defined this with the variable sizes in the very beginning. Where is it? Well, sizes is here. So we want to have 4 layers. First layer has 2 neurons, second layer has 3 neurons, third layer has 5 neurons, and last layer has 3 neurons. So this is stored in the variable sizes. And if we find the length of these sizes, this will tell us how many layers do we have. So we have sizes. It has 4 elements, which means length of sizes will tell us that we have 4 layers. And then we should store this in the variable number of layers. So number of layers is 4. Okay. How can we use this variable number of layers to update the rest of the weights and biases? Well, somehow we need to iterate through them. Does it make sense to iterate to the second layer and then go to the third layer? Well, no, because we cannot compute anything in the second layer unless we know partial derivatives in terms of the weights of the third layer. So we need to go somehow from the end towards the beginning. So we need what? We need the fourth layer. We have the actually fourth layer. We need the third layer, compute the delta of the third layer, and then use it to compute the delta of the second layer. How can we make an iteration which will do this? Well, look at this. If I say for I in range, for example, if I wanted to go from 2 to 4, I could say in the range from 2 to number of layers, because we know that number of layers is 4, so no layers. And let's plot this I, or print it. So what we get is we get second layer, index of the second layer, and we get the index of the third layer. And that's all good, but we need to have them in the other way around. So we need to get first the third layer and then the second layer. So what can I do is I can actually use the variable negative I. So I can just put a minus next to I. And what do I get? I get negative 2 and negative 3. So what does this mean? So we have, for example, our weights. So if we take the weights of the -1, this will give us the weights of the last layer. Yeah. But if I say weights of the -2, this will give me the weights of the layer before last. Or if I say, for example, what would be the partial derivatives in terms of the weights of the last layer, I get this. This is what we computed. But what we don't know is weights of the layer which come before this. So -2. So they are empty. So you can see that if I make this iteration here from 2 to the number of layers, I get exactly the right indexes to iterate through my list containing partial derivatives of weights and biases. So I will first get the number -2, which will give me partial derivatives of the weights of the layer 3. And if I get -3, then this will give me partial derivatives in terms of the weights of the layer 2. So I will be able to actually address this layer. So if I just iterate in this way, I should be able to compute delta of this layer and then delta of this layer. And then when I have the delta of this layer, I can easily compute weights and biases of this layer. When I have delta of layer 2, I can easily compute weights and biases of the layer 2. Okay, what do I do next? Well, I have this I just need to update the delta. So what will delta be? What will our new delta be? We have our old delta, which is the delta of the last layer. Well, let's look at our formula. Our formula says to compute the partial derivatives in terms of the weighted sums of any layer L, we just need to compute activations of that layer times 1 minus activations of that layer, and then Hadamard product with something else. Let's first do this part, yeah, because this is the easy part. So to compute delta, I just need to have activations of this layer negative I, which will start being negative 2, yeah, so which will be layer 3 actually. Activations of the layer 3 times 1 minus activations of the layer 3, which is negative I, which is negative 2, which is second one from the back, which is layer 3, times what? Well, let's go back to our formula, times the dot product or the matrix product between the weights of the next layer and the partial derivatives of the weighted sums of the next layer. But this weights here needs to be transposed. So if we had the layer L, now we are addressing the L plus 1 layer, yeah? So the layer after it. So let's do this. So we have dot product, MP dot product of the weights and of some delta. Well, weights should be of the layer which comes after negative 2. And what is the weight which comes, what is the layer which comes after the one before or the 3? Well, it is the weights of the layer 4. So how do we address the weights of the layer 4? Well, we would address them by saying weights of the negative 1, yeah? But then we will get the error in the next iteration because this is hard-coded. So we need to somehow show this in terms of the negative I that we are iterating through. So negative I will give us the weights of the third layer, yeah, in this case, which is negative 2. This is negative 2, or the third layer. But I need the fourth layer. How do I represent then the fourth layer? Well, I can say negative I will give me negative 2, and I need to go to negative 1. How do I go from negative 2 to negative 1? Well, I add 1. If I add 1, this will be first negative 2, but then plus 1 will be negative 1. So then this will give me the weights of the layer 4, and I need to transpose them, and I multiply them, matrix multiplication, with the old delta, so with the partial derivatives in terms of the weighted sums of the last layer, which is what delta started being with. Yeah, this is what delta started as. Yeah. Okay, now that I have this delta, it should be quite easy to compute partial derivatives of the weights and biases of the corresponding layers. So we start with the layer negative 2, which is layer 3. So the biases of this layer negative I, which is starting as negative 2, is going to be what? It's going to be the same as delta, our new updated delta. And this is a little bit more complicated. So the weights of this layer negative I, what is this going to be? How do we write these in? Well, let's look at the formula. So to compute the partial derivatives of the weights of any layer L, we multiply the delta. So this is the same delta that we used for the biases. It's a matrix product of this delta with the activations of the layer before it transposed. So we need a layer L minus 1 transposed. So let's do this. So it's going to be MP dot. It's going to have the same delta, which are the partial derivatives of the weighted sums of the current layer, times the activations of the layer before. So in this case, since we are computing the layer 3, activations should come from the layer 2. And the layer 1 should be, if this is negative 1, this should be negative 2, this will be negative 3. So activations from the layer negative 3. But again, this is now hard-coded, and this will break as soon as we go to the next iteration. So how could we describe this negative 3 in terms of negative I? So negative I will start being negative 2, and we need to go to negative 3. So what do? We simply do the minus 1. So what used to be minus I used to be negative 2, minus 1 will give you negative 3. which will actually give you activations of the layer 2. But what we need is these activations transposed. Yeah? And this, hopefully, if I did not make any mistake, which is highly unlikely, should automatically fill all the partial derivatives of the weights and biases. So let's now check what do we have in our weights and biases. Yeah? So if we now go through all of our partial derivatives in terms of weights, we see that we fill them all. Yeah? And if we also wanted to check partial derivatives in terms of biases, we can just do the same to the biases. And we get that we have filled all the biases here. So very nice. We have finished the backward pass with this one very relatively simple expression. Yeah? Okay. So now it says initialize the variable step size with a small number and use it to update weights and biases. Well, this is easy, we did it before. Step size, we'll start by making it 0.5, for example. And now we need to update the weights and biases. So the problem is the following. We have weights and we have derivatives in terms of weights. And there are lists. So we need to somehow go to all of them, corresponding matrices, and subtract one from another. So we need to subtract the derivative from the actual value and then multiply the derivative times the small step size. So how can we actually do this? Well, what we can do is we can use zip function. So I can do zip of weights and derivatives in terms of weights. Yeah, and I can just iterate through this for example, W and dW in zip. I can then print weights and then leave an empty row and then print partial derivatives in terms of these weights and then again print some separators between them. So what we have here is we have our actual weights and then we have derivatives in terms of these weights for the layer 2. Then we have layer 3, we have weights and we have partial derivatives in terms of these weights. Yeah. And what we need to do is we need to multiply this partial derivatives times the step size. So step size. We didn't actually define this. Okay, and now these are of course smaller because we multiply them by a small number. But we need to do what? We need to subtract this from this. We need to subtract this from this. And we need to subtract this from this. So how do I do this? I can just say W minus W times the step size. Yeah. And there you have it. So these should be now our new weights for the layer 2, for the layer 3, and for the layer 4. But how can we actually make this as a list? Well, we can use list comprehensions. So what do we need to do? We just need to take this thing here, put it here, and put square brackets. So what do we have? So we have W minus dW times step size for WDW in this zip. And we should have it. Yeah. So these should be our new weights. And with this should actually overwrite our old weights. So these are the actually updated weights. So we can replace the old weights with these new weights. So we will now say weights is equal to this. And we successfully updated the weights. So how can we update the biases in the same way? Well, it's the same, exactly the same thing, the same operation that we need to do. So we need to replace biases with bias minus the derivative of the bias times step size for the bias and derivative of the biases in zip, which now contains biases and derivatives of biases. And that's it. We have updated our weights and biases. Now it says calculate the forward pass again. So we know why we are doing this. We are calculating the forward pass to compare the old cost with the new cost and to see if we actually improved or not. So I just ran all the code from the beginning again to make sure that there are no mistakes in this point. So we can now calculate the forward pass. So what do we have? We have our activations, and they are starting as the D point, data point. If you remember, data point was our first data point, yeah? And then A will be this data point. Then what we need to do is we need to simply compute the last activations of the last layer. How can we do this? Well, we did it already before, so we will loop through all the weights and biases in zip of weights and biases. And then we will say that the activation will be equal to sigmoid of the dot product of weights and activations, and we will add bias term to it. And this will now go, if we print A, this will now actually update A until we get to the final value of A, which is the activations of the last layer, which is this value here. So if I now say print A, I will get the activations of the last layer. Okay, now it says compute the cost, store it in a variable C new, and compare it with the old cost. Okay, so to compute the cost, we need to do what? We need to subtract the A, which is the activation of the last layer. From it, we need to actually subtract the label, and we need to square this to get the mean squared error. And now we need to sum these three numbers, so mp.sum of these things, and we get this value. And this will be our C new cost. Now we simply need to compare the old cost and the new cost. So C old will be just C, and C new will be the new cost. And as you can see here, our old cost was 0.845 for this data sample, and now it's 0.7723. So we successfully reduced the cost or loss for our neural networks classification task. And now we are ready to do our task 4 and to implement a fully working algorithm. So we will of course have a lot of copy pasting to do here. What do we do first? Well, we need these sizes. Okay. Then we probably need to instantiate weights and biases. So where is that? Here are the biases. And weights should be somewhere nearby. Here are the weights. Then we will need our step size. Step. And we will need the length of our data. So data len is equal to length of our data. And we will need the number of layers. Let's just see how I called this before. Number of layers. Okay. Well, we need somewhere to store all the partial derivatives of weights and biases. So we need d biases and d weights to store these things. Here are the biases. D biases. And I can just do d weights quickly so that I don't search for it. So d weights is just going to be mp zeros, w shape for w in weights. And we have all of our data structures. Okay, so what do we do then? Well, we need to iterate. So for epoch in range, let's do one iteration first. How are we going to do this? Well, let's first implement online training, and then we will see later to change it into batch training. So first we need randomly chosen point from our data set. So I will call this index, and will be equal to mp random rand int of our data length. Let's print it. If I do 10 iterations, it works. Well, then our data point, d point, will be our data from this index. And then we need to reshape it into 2 rows, 1 column matrix. and we need our y, which is going to be labels of the same index, and then we need to convert this label. Convert label of this thing. So print d point y. Of course, I need an iteration here. And there we have it. We have our data point and we have our label. Okay, what do we do then? Well, we then need activations. And we will store the first activation will be data point. Or we can actually call this already, hey, this will be our first activation. Our data points are first activation. And when we store all the activations, we will put the first activation in it. Then we have weighted sums. This will be an empty array. And then what will we do? We iterate through all the weights and biases. So for w, b in zip of weights and biases. And what do we do now? We say that, for example, z is equal to m to the dot product of the weights and activations, and add to it biases, and then we store these weighted sum that we just completed, we aggregate it, we add it, append it to our weighted sums list. So append z, and then we know that the activation is going to be sigmoid of this z, and then we append it to activations. Append a. Here I forgot the dot product. Okay, this works. Let's see activations. They're all there. Okay, so this was forward pass. Now we have total cost, or cost and loss. So cost will be equal to activations of the last layer minus y, which are the labels, squared, and then summed. And now partial derivatives. So backward pass. First we compute the partial derivatives in terms of this cost. This is going to be equal to 2 times activations of the last layer minus label for this particular data point. Okay. Now we need to compute the delta. Delta is just going to be equal to dc times activations of the last layer times 1 minus activations of the last layer. Okay. And now I know that biases, partial derivatives in terms of biases of this last layer are going to be equal to this delta. And I also know that the partial derivatives in terms of weights of this last layer are going to be the dot product of this delta and of the activations of the layer before it, which is -2 transposed. Okay, now I have my number of layers. Now I need to iterate through the remaining layers. So what do? I say for I in range from 2 to number of layers. Now I need to use this negative I, no? So I need to print negative I, which will be -3 and then -2. I need to use it to compute partial derivatives in terms of weighted sums of the layers 2 and 3. Which are -2 first and then -3 from when we count from the back. So the delta is just going to be equal to activations of this negative I times 1 minus activations of this negative I. Times the dot product of the weights of the layer above it, which is weights the layer what? So negative I will give me -2, and above it should be -1. So how do I get from -2 to -1? Well, I add 1 plus 1. This should be transposed times the delta of the previous layer. when I know this, I can now fill the remaining partial derivatives in terms of weights and biases. So biases are simpler. Biases of the layer negative I will be the same as this delta that was just overwritten. And weights of this negative I will be equal to dot product of this delta and the activations of the layer before it. So in terms of negative I, this will be negative I. I want from negative 3. How do I get from negative 2 to negative 3? I say minus 1. And if I did not make any mistake here, this should be it. There is a mistake. Of course, I did not put here transposed. And now it works. Now I need to update the weights and biases in terms of the weighted sums. I can just reuse these two steps. So, updating weights and biases. And that should be it. Again, RC, or the cost for each individual data sample, is not a good metrics for telling us how our network is performing. I would need to do many iterations, and each time I would plot the cost, I will get a cost for a single data point. I cannot express the cost of the whole data set. I can do that only when we actually implement batch training. But before that, what I can do is I can compute how accurate our prediction is. So let's do that quickly. So DEF evaluate accuracy. What can we do that with? We need to loop through all the data points. So for data, label in zip of data and labels. Let's just run this function. We have our data points. So I need to say that the activation of the first layer will be this data, but we need to reshape it into a column vector. And the label will be, we'll call it Y, will be a convert label of this L. So let's print A, Y now. Okay, we have them. Now we simply need to compute the forward pass. How do we do that? Well, for weight, bias in zip of weights and biases, we need to do what? So A will be equal to sigmoid of the dot product of the weights, activations of the last layer, and just we need to add to it the biases. And we should have A computed at the end. So if I say evaluate accuracy, let me print this A here, re-indent it back. We have the activations for all the data points. I can just do this to make it clear that this is the activations for the first data point, this is the activation for the second data point, until we have the activations of all the data points. Okay, what I need to do then, I need to convert this number to either 0 or 1. So I need to round it to the nearest value, 0 or 1. How do I do that? I will call this prediction, or first let me show how I do it. I will call it mp.rint of this A. Now you have it, and I will just call this prediction. Now I'm not printing anything. So now I want to check if the prediction actually matches the label. So if mp.array equal of prediction and y, so correct. There are some correct cases, but I want to actually measure how correct they are. So I will say num correct, started with 0, and every time we have a correct prediction, I will increase this number. So num correct plus equals to 1. And at the end, I will return number of correct solutions divided by the length of our data, which is data length, if I am not mistaken. And now I get accuracy represented as a decimal number. Okay, this will do. So what do I do now? I'm gonna plot each couple of iterations the accuracy. So how do I do that? So if the epoch modulo, for example, 10 is equal to 0, which means each 10 epochs, do what? So accuracy is going to be evaluate accuracy here. And then I want to print it. So let's do 100 iterations. But I do not like this value. How can I improve this? I can just say that accuracy, I can round this number and multiply it by 100. ACC times 100. And now I can round this 4 decimal places. That's better. So now I can say accuracy is equal to whatever value it is in ACC. Let's try some different numbers for the number of epochs. Let's try 1000 and check if 100. Still not so good. Let's do 2000, 2001. We are getting a little bit better. 5001. Let's try to plot it not so often. Now you see it's getting near 100. If I try 10,000, well, I could now try to play with these meta parameters here, but before I do this, I want to show you, I want to visualize this first so that we can see maybe where the problem lies in here. So let's try to visualize this. This is the task number 5. It says apply these functions, create mesh grid and plot neural simple. So create mesh grid, we already have it. We do not have to change it. So grid is equal create mesh grid. And now to plot, we just need to compute here this score. How do we do this? We did it last time. It's just this time we have our data point here. I will call this data point now A. It's the activation. And now we need to do what? So we need to loop through all our weights and biases. W, B in zip of weights and biases. And activation will be sigmoid of the dot product of the weights and activations plus the bias. And then the score will be simply, as we did last time, argmax of this A. And we place this score. So we now need this function plot neural simple, put it here. We have weights and biases, they're fine. We have grid, we have data, we have labels, we need accuracy as ACC. Let's see what's going on. Okay, if we now run this neural network as we have defined it, we'll run 5001 epochs and we will plot each 1000. What do we get? Well, you can see that our accuracy is coming pretty high. It's like 92%. But this yellow point here is somehow beyond the reach. We cannot do much there. Question is why? Can we run it again? Will it get better? I mean, last time we were able to do it almost. Now we are getting to 92%. How can we improve this? Well, the thing is, we have defined now that our neural network has 4 layers. And the first layer is our data points, and then the second layer has 3 neurons, and the next layer has 5 neurons, and the next layer has 3 neurons. So we are practically converting here 2-dimensional point to the 3-dimensional space, which then becomes a 3-dimensional point or vector, and then to 5-dimensional, and then back to 3-dimensional. So what I'm suspecting that is happening here is that this point here makes it very difficult for the network to train if this next lever has only 3 neurons. So let me just try to increase this to 5 neurons. So we'll have 2 neurons, then 5 neurons, then again 5 neurons, and then 3 neurons. Let's see if this can help. Now, as you can see, around 5,000 iterations here, we are getting 100% accuracy. So let's try it again. Let's try to see what happens if we add even more neurons in one of the layers for the same number of iterations. As you can see, we are very quickly reaching 100%, because the more neurons we add and more layers we add, our network gets much more powerful in bending the space so that it conforms to our requirements that we put with our labels. So as you can see, now we are easily reaching this space. And what I would suggest that you try is just to try to, at home maybe, see what would be the right architecture that would do this in the shortest possible time and with the maximum accuracy. The only thing that we could maybe want to add to it is to try what happens with the batch training, because then we can definitely address the notion of total cost. So how can we change this algorithm to include batch training? First, let's make only one iteration here, and I will stop plotting for a moment because this slows down computation significantly. I'll just have the accuracy. So I want to add total cost here as well. So what do? In this one range, I need to now, in one epoch, go through all the data points once. So I will do that. For data, label in a zip of data and labels. What do I have now? I will first indent all of this. I do not need this index because I'm not anymore doing this randomly. So our activation will be this data point here, reshaped. And our label will be this L converted. This is exactly the same thing that we did last time. And then I want to introduce total cost here, which is going to be equal to 0. Okay, activations, weighted sums, and then I compute all the activations, and I compute the cost for a single data example, and I add it actually, sum them all in the total cost. I add it all to the total cost. So I add C to it. And then, of course, in the backward pass, I compute all the weights and biases. But this is not enough now. So we need to somehow average our weights and biases for our whole data set. So we need additional data structures. So where can I put them? You can just use these D biases and D weights and instantiate them now as DD biases and DD weights. So they will store derivatives in terms of biases and derivatives in terms of weights. Okay, so I have them. They're equal to 0. That's why I also chose 0 in the beginning. That's very useful. Because they are 0 when I add partial derivatives in terms of weights and biases to them, they will just become larger and larger, and then I need to divide them by the number of data points. So where do I actually update this? So right here, I have all the weights and biases done, yeah? This thing I need to put one level before in the for loop. Now that I have them, what do? Well, I need to update them somehow. So I need to make a zip of our DD weights and of our D weights. Yeah? And I will make a list comprehension. So DD weight, comma, D weight, or I'll just put it DDW and DW for DDW, comma, DW in this zip. So what do I want to do? Is I'm going through partial derivatives, and I want to add partial derivatives of weights to this variable, which will store them all. So I just need to add them together. So DW plus DW, I need to replace this with DW of weights. And I need to do the same with biases. So I need to go DD biases, DD bias plus D bias for DD biases, and D biases. So these are now storing our average partial derivatives. Yeah. Let me just check. So this is happening for each data point here. So I'm on this level of indentation. It should be in this level of indentation. That's correct. Okay, now when I need to update weights and biases, first what I need to do is I need to divide each of these by the number of data points. How can I do this? I can again make a list comprehension. So W for W in DD weights. So each of these W's is now going to be a weight matrix. Yeah. So I need to divide all the numbers within this weight matrix with the number of data points. So data length, and this will be DD weights. And I need to do the same for my biases. So DD biases will be bias divided by the data length. So this is a bias matrix for all the bias matrices in DD biases. Finally, when I update the weights and biases here, I update them with weight minus D weight from not D weights here, but DD weights here, and not from D biases here, but from DD biases here. Okay, and now each 10 iterations I will plot the accuracy. I have a typo somewhere. Where is it? It's here. Okay, I have accuracy 0%, and I can also plot the total cost. So total cost TC. So accuracy, total cost, and now let's do 100 iterations. As you can see, total cost is going down, and so is accuracy. Total cost, I want to round it. Okay, this looks a little bit better. Maybe I should plot the total cost first. Total cost accuracy, okay, and I simply need to do more iterations now. So let's try to do 1000 epochs and plot each 100. And as you can see, I'm getting to 100% accuracy when the cost goes around 1,5. Let's test this one more time. Cost is not going sufficiently enough. When it does, we get 100% accuracy, and now I can go back to plotting. Well, now it's doing it in only 1000. It depends on the starting point. Where do we start? As you can see, that's it. We have a working algorithm. It's not very fancy. It's not very well implemented yet. It's not implemented as a function. There might be easily some mistake here that we're not able to see, mostly because some of these variables that I'm using here are not encapsulated within functions. So they could be called from somewhere earlier that I'm not aware of. That's always the danger when you're prototyping. So I will just make this algorithm into a function, and from the next class we will actually see how we can use neural networks to do something productive. The examples that we did so far were about classifying between classes of points, but this was all very abstract and also very low dimensional, so our data points were on a plane, so we were able to visualize it. Next class, which is by the way our last class, I will talk more about what this all means. I want to go to a level which is beyond just how it works, but also what it does. What are the things that we will not be able to do without this kind of modeling paradigm? And also, what are the dangers hidden within such paradigms? In the next class, we will also do some applications, and we will actually do the hello world of machine learning, which is recognizing handwritten digits. So people have written digits, put them in a small square, which have a certain size in terms of pixels, and then they labeled this data. They said what digit have they written. And we have a data set of around 60,000 data points of labeled digits, and we will use it to learn how to predict if I give you a random written digit, what digit it actually represents. Since this is the last class, I will also teach you how to do this in contemporary machine learning libraries, such as TensorFlow, and what are the differences and what would be the difference in prediction quality with this network that we did all by ourselves and with the professionally crafted neural network library. So this is all for today. I hope you learned something and see you next week. Goodbye.